From the social media apps you scroll through to the navigation that gets you home, software is literally everywhere. But it doesn't just appear. It's built piece by piece through this discipline called software engineering. It's really the hidden architecture of our entire digital world. So how does this hidden world actually work? Well, let's peel back the layers. I mean, really think about it for a second. One moment, there's just a spark of an idea, right? And the next, there's a powerful tool in the hands of millions of people. How in the world does that happen? What's the secret sauce that turns a concept into code, and that code into a real, working application? You might have this image of a programmer just typing away furiously in a dark room, but honestly, that's such a tiny part of the story. Real software development, it's a structured, methodical process. It's more like an engineering journey with a map, a plan, and a final destination.
And that map, it actually has a name: the Software Development Lifecycle, or you'll hear it called the SDLC. This cycle, it guides a project from the very beginning, the planning, all the way through to maintenance at the end. So come on, let's take our first step on this journey together.
Okay, so first things first, before you can build anything, whether it's a house or an app, you have to know exactly what you're building. This right here is the foundation of any project, defining the requirements, because, you can't really hit a target you can't see. So how do you make sure everyone, the developers, the client, the managers, are all on the same page? You do it with this document, the Software Requirements Specification, or SRS. Think of it as the official contract. It is the single source of truth that details every single feature, function, and constraint of the software. But listen, not all of these documents are created equal. A vague SRS is basically a recipe for disaster. A good one has to be crystal clear. For example, it's got to be complete with no gaps. It needs to be unambiguous, so it can't be misinterpreted in a million different ways. And it has to be testable, so you can actually prove that the final product does what it's supposed to do. This document really sets the standard for success. All right, so once we know what we're building, we have to figure out how we're gonna build it. I mean, you wouldn't build a skyscraper without blueprints, right? Software is exactly the same. This is the design phase, where we visualize the entire architecture before a single line of code ever gets written. One of the most fundamental blueprints out there is the diagram. It's basically a floor plan for your data. It defines the key things, or entities, like a customer, an order, or a product, and it maps out exactly how they're all connected to one another. Let's just break down the basic grammar here. The entities, the main objects, are shown in rectangles. Their properties, or attributes, are in these ovals. And the diamonds, those show the relationships between them. So for example, a customer places an order. It's a simple visual language, but it describes a really complex data structure. Now let's look at another kind of blueprint, the data flow diagram. If an diagram is the floor plan, then a DFD is kind of like the plumbing and electrical schematic. It doesn't really care about the structure of the building. It just shows how data moves through the system, where it comes from, how it gets processed, and where it ends up. And here's a perfect example. This is called a zero-level DFD, which gives you that 30,000-foot view. You can see at a glance that customers send an order into the online shopping system, and then they get a delivery back. It's super simple, it's clear, and it tells you the main function in an instant. Okay, but for more complex systems, we're going to need a bigger toolbox. And that's where UML, the Unified Modeling Language, comes in. It's not just one type of diagram, it's a whole standardized set of them. This lets everyone involved look at the project from all these different angles, from how a user interacts with it to how it's physically deployed on servers. And these diagrams fall into two main categories. You've got structural diagrams, which, like the name suggests, describe the static architecture. The parts of the system, like a blueprint showing rooms and walls. Then you have behavioral diagrams, which describe the dynamic stuff, how people and data actually move through those rooms. Put them together, and you get a complete picture. So we've got our requirements, we've got our blueprints. Now, how do we actually manage the whole construction process? Well, turns out there isn't just one way to build software. Let's take a look at a couple of the most common strategies, or what we call process models. First up, we have the classic, the waterfall model, and it's pretty much exactly what it sounds like. You complete one phase entirely, like getting all the requirements, and only then do you flow down to the next phase, like design. The key thing is you can't go back upstream. It's a rigid, step-by-step approach that's still used for projects where the requirements absolutely cannot change, like in aerospace or medical device software. So what's the upside? Well, it's simple and it's easy to manage, but only when you know exactly what you're building. The huge disadvantage, though, is how rigid it is. There's no room for customer feedback or changes until the very end, which makes it incredibly risky for most modern software projects. If you misunderstood something on day one, you might not find out for months. Yikes!
And that risk, that massive risk, is precisely why most teams today use something called the Agile model. Agile is basically the philosophical opposite of waterfall. Instead of one big launch at the end, you build the product in small, incremental pieces, called iterations. It's all about flexibility and constant collaboration, letting the team adapt to new user feedback and changing requirements on the fly. It is truly built for the modern world of app development.
So, whether a team is using waterfall or agile, they eventually have a product that's been built. But guess what? The job is not done, not even close. How do we know it actually works? And not just that it works, but that it works correctly. This brings us to the absolutely crucial phase of testing. Two really key types of testing you'll hear about are alpha and beta. Alpha testing is done in-house by the company's own employees, who are hunting for bugs before the product is ever seen by the public. Once it passes that stage, it moves to beta testing. That's where a limited number of real users tested in a real-world environment. This is the final dress rehearsal, and it's basically the firewall against a disastrous launch day. And finally, let's talk about the thing that separates pretty good software from truly great software. It's not just about having cool features. It's about the quality of the underlying architecture. It's about building something that is clean, efficient, and easy to maintain for years and years to come. Two key principles guide this: cohesion and coupling. High cohesion is a good thing. Think of it like a well-organized kitchen drawer where all the spoons are together. Each module of your code has a single, well-defined purpose. Low coupling is also a good thing. This means your modules are independent, like separate kitchen appliances. You can replace the toaster without breaking the microwave. If you change one part of the code, you don't want the whole system to come crashing down. At the end of the day, getting this balance right, making sure your components are both super focused on their job and independent from each other, that's the real secret to creating software that is robust, scalable, and easy to work with. It's the hallmark of excellent engineering. So there you have it. From a simple idea to a finished app, it's a journey of specifications, blueprints, build strategies, and quality checks. Every single button you press, every feature you use, is the result of countless choices. So next time you open up your favorite app, just take a second to wonder, what choices were made here? What kind of blueprints do you think are holding it all together?